Okay, so the first major change is that we can now report on what's in each tube before we do the run. So what I've done here is set things up so that we've got all the original chemicals, all the primers, the dNTPs, the polymerase, the buffer, and so on. And instead of pipetting all of those in the right proportions into each tube, I've created 3 tubes just to make everything a bit quicker. And also to make things quicker, when I create a plate, it just creates a plate with 3 wells. And this is just for testing purposes. So let's open the 3 pre-prepared tubes and put 20 microliters of each solution into the wells. And then once we've done that, let's take this over to the PCR machine. Now on the PCR machine, what will eventually happen is you'll be able to click on this screen and then the settings will come up. But let's click on settings for the time being. This is what you've seen before. The student puts in various numbers for the temperatures and the times. They check that things are in range and then they click done. So they're ready to load the plate. So they load the plate. Now, I should point out that at any stage they can have a look to look at the composition of the wells. So by clicking this button here, you get a report of what's gone into the wells. So I can actually copy that and put that into an Excel spreadsheet. So let's pop that over here. So basically for each of the wells along the top, we've got the concentration of each of the components, so that if anything happens that is a bit unexpected, if there's been any contamination, what have you, it'll show up on this table. So then we've loaded, we start, and I could make it more of a gap here. At the moment it happens almost instantaneously that all 40 cycles have run, but we can now look at the products. And again, we get a spreadsheet. So let's copy that and put that into Excel as well. So this is our list of products. And what we see now is that for each of the tubes, and this actually should be over here, for each of the tubes, we've got a particular combination of forward and reverse primer. So we've got forward one, reverse one, which would give an amplicon size of 298. And because tube number 1 has both of those primers in it, in good amounts, you get plenty of that amplicon produced. But you don't get any of this amplicon produced in tube 1. In fact, you don't get any of this amplicon produced in any of the tubes because there are none of the tubes that contain lots of forward 1 and reverse 2. And so each of the combinations is processed and by the sort of chain reaction algorithm that does the multiplication each cycle. And you can see that in tube number 2 we do get a product. It's a product of forward 2 and reverse 2, and of course that's because those are in there. In tube number 3 we get only a tiny bit of this product. Now the reason why we get only a tiny bit, despite the fact that there's actually plenty of the forward and reverse primers there, could be to a number of reasons. It could, but looking at it, it looks like it's most likely to be that there is quite a lot. This is quite a long amplicon, and perhaps if we gave it more time, it would work better. So in fact, let's try that. So the first nifty thing is that we can recycle this plate, which basically means that we can completely get rid of all of the amplifications and go back to what the constituents were when we set up the wells. So that allows us to experiment with lots of different permutations. So this time let's do the settings so that we have a longer amplification time. Let's really crank it up to 60 and then click done. And I think then we should load and press start and see what products we get this time. And look at that, we now get plenty of the forward 3, reverse 3 prime product. So that's really fantastic, that ability to recycle the plate, go back and change conditions and see different products being produced. And we haven't had to run this on a gel to do that. We're actually just getting the list of products that are made. And that's done numerically. So if one product is really dominant on a gel, you might not see some of the fainter tracks, whereas you see the numbers on here. Now, ultimately, of course, those numbers are going to be translated into a gel pattern, but for the purposes of feedback and for the purposes of our testing, this works really well. So let's recycle everything and go back to the settings, and let's just take this back down to 30 seconds, I think it was. Let's now take this to 52 degrees. So this is quite a low annealing temperature. And this time when we load and we start and then we look at the products, whoa, we've got a lot more products here. You can see that in addition to all of the primers that we had before, creating different amplicon sizes, we've now got a whole bunch of new ones. And those new ones are based on the old primers or on the original primers, but because those primers have now bound more promiscuously, we've got more different amplicons that are going to result. And if the original primers are present in the tube, we'll get product from those. So we've got extra forward binding sites, that's what this A represents here, and we've got extra reverse binding sites. And in fact, they can apply in combination. So here we've got the extra forward one and the extra reverse one as well. And because these primers were present in the tube, we've got tons of that amplicon as well. So a couple of really big things have happened. This ability to record the well constituents, the ability to recycle, the ability to get lots of different reference to TMs for each of the primers and generate more and more off-target binding, which results in more amplicons. And of course, the ability to see exactly what's produced in each tube as a number, so not just as a band on a gel. Of course, there will be a band on these, will be put into bands on gels, but the really important thing is that we're able to get a sense of exactly what is being produced. So that is that's sort of what you can see as a result. There's a couple of other things that have happened underneath the bonnet there. One is that I've introduced a much tighter dependence on the DNA polymerase activity, so that what the student adds to the tube is taken care of. There's a dependence on the level of the dNTPs, which there wasn't before. But two big things that I've still got to do. One is to make sure that each cycle we're keeping track of the primer use between reactions. So at the moment we're keeping track of dNTPs and primer concentrations within a reaction, but we need to do that across reactions within the same tube. And the other thing that is that's really starting to become clear now is that the way that we set up all the identity of the forward and reverse primers and their TMs and the amplicons that they produce, this is now looking like something that should be in a database, and that database is something that is changeable by the course coordinator, And so that completely makes it possible to design whole projects and maybe even link to actually known bioinformatic data sources. So if you know that a particular primer, a pair of primers produces a particular product, then that may be able to come from the bioinformatics site directly into this. So not talking about making this something that does any bioinformatics, but something that responds to intel that you've got from a dedicated primer design or primer exploration sort of site. So those are the advances that are made. Those are the next steps. And yeah, pretty pleased about the way this week's work has gone.